In section 3.4, we will cover problems that we would refer to as optimization problems. So the problem is going to somehow present a situation where we want to optimize, i.e. find a maximum or minimum type value. And as a motivating example to help us think of the general procedure we can apply, let's consider the very typical example. A farmer has 2,400 feet of fencing and wants to fence a rectangular field that borders a straight river. So he needs no fence along the river. And what we want to answer is a question, what are the dimensions with the largest enclosed area? So the first thing to do is to read the question carefully and then somehow encode that relevant information into a picture. So we have a river, and along the river, the farmer is going to build a rectangular fenced-in area. And what we would like to know is, or think about here, is what quantity do we actually want to optimize? And the key statement here is, what are the dimensions of the field with the largest area? So the area is the thing that we want to make as large as possible. So we need to label somehow all relevant variables. So we can think of maybe x as being the length of the fencing coming away from the river, so it will be the same on both sides here. And then y. So if we do this, we would say that the area, the thing that we want to optimize, is x times y. And this is a very typical situation to be in. You draw a picture, label the quantities, write down the function you would like to optimize, but the problem is it involves more than one variable. In order to apply calculus, i.e. differentiate, find the critical points, we need a function of one variable. So once we've written down the quantity that we are going to optimize, we have to think what other information in the problem will allow us to reduce this down to a single variable. And the key fact is that there is 2,400 feet of fencing, and that is giving us the perimeter of the region which is fenced in. So 2,400 is the perimeter of the fencing, which is 2x plus y. And now I can very easily solve for the y variable. So y is equal to 2,400 minus 2x. And once we've solved for that y variable, we can just plug that back in to the function that we would like to optimize. And I can now say that a, as a function of x, is going to be x multiplied by 2,400 minus 2x. And I also want to think about the size that x can be. Well, looking at our picture, you say, well, maybe unrealistic, but x could be 0 at its smallest. And at its biggest, since you have to go out from the river and back in, it could be half of 2,400. So in this case, we would say that x is in the interval from 0 to 1,200. And we want to know what is the global max of this function in that interval. So before differentiating, let's simplify 2,400x minus 2x squared. And what we've done at this point is we've reduced this down to a familiar problem. How big can this continuous function be on a closed interval? Think about the problems we encountered in section 3.1. That absolute or global maximum is going to occur at an endpoint of the interval or somewhere in the middle. So let's differentiate and find the critical points. That's somewhere in the middle. A prime of x is 2,400 minus 4x, and I would like to know where is this first derivative equal to 0. So 2,400 is equal to 4x. So x is equal to 600, which is our critical point. Now, in order to determine if this critical point is going to correspond to a local max, local min, or even global max and min, we can make a number line, as we did in previous problems. So we think 600 is our critical point. We're looking from 0 to 1200. And I want to know what is the sign of this function a prime. Well, looking at the function we have, 2400 minus 4x, if I plug, let's say, 0 in, we would get back something positive. So our function is positive, our a prime, to the left of 600. If I plug in something to the right of 600, let's say 1000, then we would have 2400 minus 4000, which means a prime is negative. And now, if we think about what's happening at 600, our function is increasing to the left of it and decreasing to the right of it. So the only possibility is that it has to be the global maximum. So the observation is that we have a global maximum at x equals 600. And then we just have to make sure to go back to the question that we've been asked and make sure that we're answering it. What we've been asked to find are the dimensions of the field with the largest area. So the largest area corresponds to when x is 600. So 600, but what is y? And at this point, we always go back to that bit of information that we use to reduce the variables. So y is 2400 minus 2x. So in this case, y is 2400 minus 2 times 600, which is 1200. So the global max occurs at x equals 600, and so our conclusion then would be the dimensions of the field with the largest area are given by 600 feet by 1200 feet. Now, in terms of this procedure that we've been used, it's something that we can actually easily replicate in future problems. I think of it in terms of the following steps. We read the problem carefully and we draw a picture that allows us to encode all of that relevant information. We assign variables to those important quantities. Whatever quantity we want to maximize or minimize, we write a formula for that function. In the previous example, it was writing down a formula for area. The typical thing is that function q is going to involve more than one variable, so we use some conditions from the problem to reduce it down to a function of one variable. Then it becomes a familiar problem. You find the critical points, and then you somehow classify with your derivative tests.